Hey guys, this is chapter 20, video 2. I'm picking up, we just talked about the reaction between zinc and copper, where you put a piece of zinc into a copper solution and a redox reaction can occur. If we want to set up an electrochemical cell, what happens is we set up two separate vessels. Sometimes they're connected, sometimes they can be two beakers that are entirely separated from each other. A few key components here. The zinc cell, we're going to have a piece of zinc metal that we stick that in. That's going to be our electrode. We stick the zinc metal into a solution that contains zinc plus 2 ions. There's usually some anion present also, but that's going to be a spectator ion. And then I'm going to have, that's one cell. The other cell, I'm going to have a piece of copper metal stuck into a copper solution. Okay, so in each cell I have the metal and a solution with the ion of that metal both present. Okay, now we said previously that zinc wants to get oxidized and copper gets reduced. So when that happens, the zinc being oxidized, the side that is losing electrons, we call that the anode. Just remember, oxidation is the anode. And then the reduction is going to happen in the cathode. So oxidation, anode, they both start with vowels. Reduction in the cathode, they both start with consonants. That's a trick to remember them. But in the anode, the oxidation, some of the zinc atoms are going to give up their electrons from the surface of the metal. The electrons can flow through the metal to the wire, and they need to leave this half cell, go all the way through the wire over to the copper, and when it gets to the copper, it's going to go all the way to the surface of the copper, and when one of these copper plus 2 ions comes in contact with the surface, it's going to gain 2 electrons, and it's going to turn that copper ion into a neutral copper atom. So there's a flow of electrons that occurs from the zinc metal all the way to the copper ions in solution. Okay? The anode is the source of the electrons that flow through the wire to the cathode. When the electrons move, that creates a voltage. And if we actually hook up a voltmeter, we can measure the voltage of the cell. And for a standard cell between these two, the voltmeter would read 1.10 volts. We'll get into those measurements in a little bit. But for now, this is the electrochemical cell. The only thing that's missing from this picture is that if we have a flow of electrons from one half cell to the other, if that flow is the only thing going on, it would create a buildup of negative charge in my cathode. If we build up charge over there, that would stop the flow from occurring. So we actually have to have one more thing. We have to have something connecting the two solutions that's called a salt bridge. And basically the salt bridge will allow some of the other ions in solution to flow through the salt bridge. Sometimes it's a tube, sometimes it's just a piece of like filter paper or something is what we actually use in our lab, where we lay the filter paper across, and as the filter paper soaks up water, some of the ions can flow back and forth between the solutions, and that's going to maintain electrical neutrality. If you don't have a salt bridge there, the electrochemical cell actually won't work. You won't get any flow of electrons because it'll very quickly build up charge on one side, and then it'll start pushing the electrons back the other way. So, in my two half cells, first of all, on the left side of the equation, and it's always written the same way, I'll go back for a second. When we write an electrochemical cell, the anode, the oxidation, is always supposed to be written on the left. The cathode is the reduction, is always written on the right. So when I go to the next slide, on the left side is the zinc reaction, that's the oxidation. Zinc, the metal, is giving 2 electrons away that flow through the wire. That turns zinc into zinc plus 2. These ions can float off in the solution. The electrons go through the wire. When it goes to through the copper electrode, gets to the solution, copper ions in solution are going to absorb those 2 electrons and become copper metal. So as that reaction occurs, if I look back at the electrodes, the zinc electrode is going to be slowly dissolving into solution. while the copper electrode is going to actually be gaining copper from the solution. So if we were to, over time, weigh the pieces of metal that were stuck in the solutions, the zinc electrode will lose mass, the copper electrode would gain mass. Now, I can add each of these reactions, describes what's happening in one of the cells. Basically, you can't have one of these reactions happening without the other. So we call, this is the oxidation half reaction. This is the reduction half reaction. When we put them together, that creates the overall reaction that's occurring. This is the reaction that's occurring in our electrochemical cell. So the electrochemical cell includes both of the half reactions that are going on. Okay. When we look up in a few minutes, we're going to look at the reduction potentials. For each half reaction, there's a certain potential for that reaction to occur. We measure that as a voltage. So there's a voltage associated with this reaction, there's a voltage associated with this reaction, and by Hess's law, if I add these two together, I should be able to add together their voltages, called the reduction potentials. I can add them together to get the overall voltage for this electrochemical cell. It's called the cell potential. If we're doing this under standard conditions, and if you remember from the last chapter, standard conditions would mean that all the aqueous ions, so the zinc plus 2 is going to be an aqueous ion, the copper plus 2 is going to be an aqueous ion. If they were both 1 molar in concentration, those are standard conditions, then that would mean that the E value, which we put E with the naught symbol, that's the standard cell potential for this reaction would be 1.10 volts. So all of these numbers are for standard conditions. If we change it from standard conditions to non-standard conditions, that would mean we take away the naught symbol and we'll have to do a little bit different calculation in that case. Okay, now, the E value is 1.10 volts for this reaction at standard conditions. It's important to realize that the E value, in order to have a spontaneous reaction, like if I want to write a reaction that's actually going to occur, I need to have a positive E value. Why is that? Well, there's an equation that relates delta G to the E value, which is called the electromotive potential. Sometimes it's called EMF. But the E value has to be positive so that when N is the number of electrons being transferred, F is called the Faraday constant. It's 96,500 something. It's on the formula sheet. But in F and E, if they're all positive numbers, the equation has a negative here. So 3 positive numbers times the negative is going to give me a negative delta G. In order to have a spontaneous reaction, that's what I need. I have to have a negative delta G there. So just remember, a positive E value corresponds to a negative delta G, which gives you a spontaneous reaction. So here's a more realistic picture of an electrochemical cell between zinc and copper. Again, the zinc half cell has the zinc metal as the anode, so that's one of my electrodes. It's dipped down into a zinc solution where zinc plus 2 ions are present. The other electrode, copper, is dipped into a copper solution where I have copper metal in the electrode and copper plus 2 in solution. That allows the two half reactions to occur if I connect them with the wire. And then I also have the salt bridge in between where the other ions can move through as they need to maintain the electrical neutrality. Now, each half reaction has a certain electromotive potential to occur. Those are listed in the appendix of your book. So these are all written in the form of reduction. So if you decide that an element can be oxidized, you actually have to take the reaction and reverse it. When you reverse the reaction, you're going to change the sign of the standard E value that we're going to look for. So in this reaction, I had the zinc reaction. Here at zinc plus 2 gains 2 electrons to form zinc metal. That's the reduction reaction for zinc. In our cell, we said that the zinc was going to be oxidized. If you look back at the reaction, it should actually be zinc solid on the left side reacting to form zinc plus 2 and 2 electrons on the right side. So this value that I look for, negative 0.76, that's actually the opposite of what I was doing in my reaction. So I'm going to change the sign of this one to positive 0.76. For copper, copper plus 2 gains 2 electrons to become copper metal. That is the half reaction that we were doing a minute ago, so that one can be left as it is, 0.34. So if I get the two half reactions, I have to combine them in the right way to get the overall EMF value for the electrochemical cell when I build it. So, a few little details. When I add the two half reactions together, that's an application of Hess's law. If I can add the reactions together, I can add their E values together also to get the overall E value for the reaction. If I do reverse a half reaction, I had to change the sign. Now, I'm going to show an equation in a minute that instead of changing the sign yourself, we're just going to get the value from the table and then subtract it from the other value. If you subtract the value from the table, that's the same thing as changing the sign. So just make sure that you practice these enough times that you can get that down. When we add two half reactions to get a cell potential, if we want it to actually be the reaction that's going to happen, meaning we assign the anode where oxidation is, and we know electrons are going to flow to the cathode. If we want electrons to flow the way we want them to, then we need to make sure we have a positive cell potential. Because if the E value is not positive, then that reaction is not really going to happen. The electrons will actually want to go the other way if you have a negative E value. And then finally, a trick when we get into balancing the equation, sometimes one of the half reactions, we're going to have to double the reaction or triple the reaction before we add them together. The key is when we add them together, it's going to be important that we have the electrons canceling out. Well, in thermochem, when we double a reaction, the amount of heat that's involved is going to double as well. But in electrochem, that's not true. In electrochem, the E value measures the potential for something to be oxidized or reduced. If I double or triple a reaction, it doesn't change how easily it's oxidized or reduced. So E values, even if I double a reaction or triple a reaction, I'm not going to change the potential that I get from the table. Okay, that's a key thing to remember. Don't mess that up. And then a few more things. When we set up a cell, you got to remember we have to have a salt bridge. When we start looking at batteries and stuff like that, if you look in your car, there's the red terminal and the black terminal. Sometimes on a battery, there'll be a positive electrode and a negative electrode. It is important that you guys recognize that. So the red electrode is reduction. Red reduction, that makes sense. It's when you draw the electrochemical cell, it should be the one on the right side. It's labeled as the positive terminal, and it's called the cathode. You need to know the connection of all those things. Then if we look at a battery, the black electrode on a battery is the oxidation electrode. That's the anode. It's on the left side of the electrochemical cell, and it's the negative terminal on a battery. So know everything that connects to the anode or oxidation. Okay? And then finally, you need to remember that electrons are always going to flow. If you have it set up right, they're going to flow from the anode where oxidation occurs. They flow through the wire to the cathode, which is where reduction is occurring. So, if I had a reaction and I asked you, okay, zinc is going to be oxidized, silver is going to be reduced, what would the standard cell potential be for this electrochemical cell? How would I calculate E naught? The answer is I'm going to look back at my reduction potential table, or look in the appendix, which is what the next click is. Look back at my table of reduction potentials, and then I'm going to plug in the equation. The E of the cell, which is the whole reaction, is going to equal the E of the cathode, which in this case, cathode's reduction. That's going to be silver going from +1 to 0. So that if I look up the value for silver, it's going to go right here. And then the zinc value, if you look closely at the table, the half reaction in the reduction potential table is going to be backwards from this one. Here I have zinc going from 0 to +2. If I look back at the table, it's going to have zinc going from +2 to 0. That tells me that this is going to be the oxidation. If I use this equation though, I want you to just get the two numbers from the table, plug them into the equation, and don't change the sign. That's what the subtraction is for. If I subtract the anode value that I got from the table, I don't need to change the sign. If you change the sign and subtract, you're double dipping. You end up putting it back to the value that you started with, which is no good. So if I look at the E of the cathode for silver, I'm pretty sure in the table that was 0.80 volts or 0.799. So I plug in 0.799 for this one. The anode for the zinc, I'm pretty sure, I think it was 0.3, let me see. So the silver one was 0.80, and that's the reduction. That one was good. The zinc one is negative 0.76. So I'm going to take that negative 0.76. I'm plugging in negative 0.76 right here. So I'm going to have 0.80 minus negative 0.76. Well, if I do minus and negative, that's where my sign gets changed. It's going to be 0.80 plus 0.76 to get the value, which is going to be 1.56. So the E naught for this reaction should be 1.56 volts. And the key there, by subtracting the anode, that changes the sign for you. Don't change it twice. Now, last thing we'll do here before I cut off, if I'm doing a reaction at non-standard conditions, it's a lot like in the last chapter we did delta G. Delta G, we found delta G naught, and then we plugged that into a bigger equation to find delta G without the naught symbol. We have an equation just like that called the Nernst equation. I'm going to have to cut off. We'll pick that up in the next PowerPoint or the next